just ask me question right then. Whatever you don't understand, just ask me question right then. If you don't get the chance to ask the questions, come to my office hours, 1:30 to 2:30, or I have posted all of the time, posted in black. So just come there, and still if you cannot understand the topic, now with the office hours you can ask any questions. You can take as long as it takes for you to get to understand the concept. So you can come multiple times, that's not a problem. Now if you still don't understand because of my explanation, you can take a different point of view, so you can go to the TAs. Right? So you can come to the TAs and ask questions, and if still they cannot resolve, then what I can do is, apart from the book that I am using, Galvin, I can suggest you some other books that you can you may want to read. Right? So that is with respect to that student's query. Now the thing is, the initial part of the course is a bit difficult to understand, because I am assuming some background knowledge on how compilers work, how functions are executed, and so on. So those are principles of programming language concepts. So for that, what I'm going to do is, this Monday we have a recitation. I will go to that recitation, and we will explain whatever background concepts we need to understand the first few classes. Right? So I will go to recitation, but if all of you come, then that will be a big problem. So what I will do is, I will record the class and post in the platform. So if you can't make it, that's fine. And please don't make it. Whoever enrolled for that class, make it. Because there are only 34, 35 seats. And so if all of you make it, then that's will be a big problem. So let's start our discussion, unless you have any questions. The project, I will update the date today. You will get at least 3 weeks, and if needed, we can extend. But for now, 3 weeks I'm thinking. Yes.
So are you assigning the project now?
Today the TA is going to assign. It will be assigned today. So from today, 3 weeks. Now, and we'll see at the end of maybe 2.5 weeks, because that's when you start writing the project, right? So around 2.5 weeks mark, we'll see how many of you have started, and then we'll go from there. Maximum we can extend by 1 week, not more than that. So we'll see. Now let's recap what we talked about. So we are talking about controlling program behavior. And there are two aspects for controlling program behavior. First one is, we should not allow program to write on any part of the memory. It should be restricted. The second one was that we have to limit the time for which a program runs. And so these two were the motivation to have some sort of a manager in our system. Now that is not yet operating system. We call it resident monitor. What is the difference? We'll see in a little bit. So we said that okay, there has to be a manager, but then the problem is, who says that a program has to obey the manager? Right? There is no control. Even if we put a manager there, there is no control. Program may ignore the manager. So that's why we studied two concepts: CPU protection and memory protection. Using these two, we can enforce a program to always obey the manager, the resident manager. So how did we do CPU protection? We said that okay, there are two modes. There are two modes: user mode and kernel mode. Right? And these two modes have certain restrictions. So in the kernel mode, you can execute any of code that you want. You can write on any part of the memory that you want. But in user mode, you cannot execute certain opcodes, right? And hence you cannot run certain write on certain part of the memory. So that restriction we imposed. Now, how do we impose such restrictions? We impose such restrictions using system calls. So we said that okay, user programs cannot run system calls. Now, even if we say that user programs cannot run system calls, that doesn't do it. We have to have a mechanism to prevent user programs from running system calls. So the first step to do that is to understand whether, how do we understand that a particular program is user mode and a particular program is kernel mode. So we say that a program has a lot of registers associated with it. In order to run a program, we have to have a lot of registers. One register is program counter. The other register is status register. These two are very important, and there are many others. Now, for example, there is stack pointer, then there is heap pointer, all those are registers. Right? So that is different. But these program counter and status register, these two are very important. What does the program counter have? Program counter register. The program counter register has the address of the next instruction that you are going to run. And if we put the first address of the or address of the first line of code of that particular program into the program counter, then it runs. What does the status register have? Status register has a lot of things, but one thing that it has is the mode bit. If that mode bit is 1, then the program is privilege mode or kernel mode, and if the mode bit is 0, then the program is user mode. So that's how we differentiate that a particular program is user mode or a particular program is kernel mode. That's how we differentiate. Now then we said that okay, still there is a problem, that how do we switch between user mode to privilege mode and then privilege mode back to kernel, back to user mode, right? Because if we don't switch, then what we are saying is that a user program cannot run system calls, because all system calls are privilege mode. Right? So we are saying that user program cannot run system calls. But then that directly contradicts with our idea that a user program should take permission of the resident monitor to read the input. Because in order to take permission from the resident monitor, user program has to run system calls. So then we ask the question, how do we enable user program running system calls? So we have to have mechanism of switching. So when we studied the mechanism of switching, we said that system calls are functions, but there is a subtle difference between the normal functions that we run in our program and system calls. What is that difference? The difference is that in normal functions, what do? We put the arguments in the stack and then we call the address of the first line of code for that function. That is what we do in normal function. For system calls also we do the same things, but there is one extra step. There is one extra step, the switching between user and privilege mode. So how do we do that? We took the example of printf and we saw how we do it. So printf, what it does is that it does the same things as taking the argument, putting into the stack, but instead of running or calling the first or address of the first line of code, instead of doing that, what printf does is that it takes a unique number, right? It takes a unique number and puts it into the R0 register, and then it stops. It cannot run it. Why? Because we are forcing the printf function to not execute whatever is there in R0. How do we do that? We studied later that we do it using memory protection. Why? Because there is a mechanism that tells a program that you can only write or do whatever you want between X and Y. Right? So memory protection says that okay, this program cannot do whatever it wants in R0. But now we say that resident monitor takes over. So resident monitor is privilege mode. So it can write in any part of the memory it wants to. Right? So since resident monitor is privilege mode, that monitor can go into R0 and execute the syscall code. Right? So that's how we stop printf from executing whatever code is there in R0.
So can you write to the R0 register from user mode?
Yes, you can write into the R0 register from user mode, but you cannot execute whatever is there. So then what happens is that the resident monitor takes over, it runs our whatever syscall code is there. So we said that there are several tables, right? There are several tables in the operating system. One such table is the system call table. So for every system call there is a unique number 0 to something, right? So the number 3 is for the system call write. Right. So now printf takes the number 3, puts it into R0, stops. Resident monitor comes in, sees that number 3 is in R0, then it does one thing. It goes to the table and understands that 3 means call write. Right. Write is a function that only resident monitor can execute. Now in that function, what is there? What is there in that function? In that function, it uses interrupts. That is another very important concept in operating system. We need interrupts, and we saw why we need interrupts in previous class. So in the call write function, in the write function, there is an interrupt. What interrupt? Again, we know that with respect to every interrupt, there is a number. And what does that number correspond to? That number corresponds to the interrupt vector. What do we have in the interrupt vector? Lot of things. The address of the first line of code of the interrupt service routine, the status register of the interrupt service routine, and many more. Right? So this write function, in it you have the code int x80. Int is the opcode for interrupt, and x80 is the number that corresponds to the interrupt that writes on the screen. Right? So the resident monitor then calls this interrupt, the interrupt writes on the screen, and that's how we have printed. So now we see that that's how we can switch between user to privilege mode. So that is CPU protection, right? Because we are not allowing printf to execute whatever it wants, only resident monitor executes. So that is CPU protection. But then when we have CPU protection, what are we assuming? We are assuming that printf cannot execute whatever is there in R0. Only resident monitor can. R0 is a register. Register means it's memory. So that means we need memory protection. If we don't have memory protection, then the printf function should have executed whatever is there in R0. So there is no user mode, no privilege mode. So in order to have that user mode and privilege mode, we need memory protection. How do we do memory protection? Very simple idea. You have a memory management unit. You want to restrict a program to only write between X and Y. So you have a memory management unit. Every time a program tries to access an address M, the memory management unit checks two things. It has two registers, a base register and a bound register. Right? So you send an address to the memory management unit. The memory management unit checks that, okay, is this address greater than X, which is the base register, and is it less than base plus bound? If that is the case, it allows the program to do whatever it wants. If that is not the case, then it restricts. Okay. Now the question is, in memory protection, you need two registers, base register, bound register. Can I change it? Can user programs change it? Turns out no. Only resident monitor can change base and bound register. So how do I ask resident monitor to change base and bound register? I use system calls. Right? I use system calls and I request the resident monitor. If the resident monitor sees fit, that okay, that's fine, you can have some more memory, then I get it. Right? So then, this base register, bound register changing has to be done through system calls. So that means it needs CPU protection. So that's how CPU protection and memory protection go hand in hand. You cannot have one or the other. You have to have both together. Right? So that's where we stopped last time. Let's continue from there. So that these slides give an example of different types of interrupts. There are clock interrupts, device interrupts, keyboard, mouse, network, and so on. So just to summarize whatever we have talked about, we are going very close to the end of the module 1. And I think we will finish module 1 by today. So the exam for module 1 will be on next Friday. So I'll give an announcement for that. So we have talked about different efficiency methods. automation, overlapping of I/O, spoofing, buffering, all those things we have already talked about. So having next Friday exam is not good. We need more
Maybe
time.
if you make it open book.
I want to do a test because a lot of students are saying no open book. So I
Oh,
don't- Okay, let's discuss this issue because there is some problem. So a lot of students are planning their travel. So they are telling me that maybe just having a fixed day of the week, if we have exam on a fixed day of the week, that's better for them for planning for travel. So I said that maybe Friday, we take Friday as the day where we take exams, right? So if that is the case, then if you don't want an exam this Friday, because I understand it's the start of the class and you are still getting out of holiday mode. So what we can do is we can delay the module 1 exam to, instead of next Friday, we can do the next Monday for just the
Yes.
module 1.
Just the module.
Right?
Yes.
For just the module 1. For all other modules, we will have Friday exams because that will help other students to plan. Yes.
For the module, for the exam, do we have any type of study guide or?
Lot of study guide I will give you. So if you go to the homework questions, there are tons of questions that you can practice on, right? But yeah, I'll talk about that. So then I'll post an announcement that it is not next week, but the following week, Monday. And these exams are going to be short, so it won't last the whole class. So maybe the first 20 minutes of class will discuss some of the syllabus contents, and then the last 30 minutes of the class will be an exam. And so these are very short exams, so it's just 10% of your grade. But even if it is 10%, don't neglect it.
How many questions are you thinking about it? So if you're doing.
I am thinking that one big question where you have to have an analytical answer and some multiple choice questions. That's what I'm thinking. I'll give you examples, enough examples. Okay, so let's continue our discussion. So we are summarizing what we did for module 1. So we talked about efficiency, spooling, buffering, multitasking. We didn't really talk about multitasking because we are saying that in this course we won't really talk about multiprocessing. So multiprocessing we won't really talk about. But multitasking and multiprocessing are a little bit different concept. Multitasking means you have a lot of processes and you run them together. Multiprocessing means you have a lot of processes, also you have a lot of resources. And you run processes in different resources. But we are not talking about multiprocessing. We will talk about multitasking. Multitasking means you have one processor and you have many threads that run on that processor. Right? And you switch between them. So we will talk about that. Now, whatever we have talked about. So we have talked about interrupts, we have talked about system calls, right? And we have talked about peripherals, the CPU registers, all these things we have talked about. All these things combined forms what is called kernel. Right? So if we talk about Linux kernel or Windows kernel, kernel is a collection of system calls, it's a collection of interrupts, it's a collection of drivers. So drivers, interrupts, system calls. These three things are part of kernel. So here if you consider, so we have interrupts, we have system calls, we have the hardware, which means the things that are actually connected to the CPU, right? And these hardware have drivers, which is the software. So what is a driver? Anybody knows what is a driver for a particular hardware piece? What? No. What?
I think of them as bridges.
Bridges. So the first level of abstraction. So if I give you a hardware, a piece of hardware, let's say I throw a CPU at you, right? What will you see in that CPU? You'll see pins, right? Pins coming out, right? What do you have in those pins? What do you do with those pins? If I just give you a CPU, you can do whatever you want with those pins. You can run Microsoft Word in that CPU. But the problem is you have to know the configurations, the pin configurations. You have to give it bits, ones and zeros on those pins. Now that is a very difficult task for any common user. Right? I don't know what pin configurations I need to run Microsoft Word in the CPU. Right? I don't know. So there has to be some abstraction. Abstraction means you convert this pin configuration into something meaningful, something that I can understand. So what do we understand? We understand functions, right? We understand init, we understand start, we understand stop, right? So drivers are the first level of abstraction that converts these pin configurations into functions, very basic functions. Right? So those are drivers. Now these basic functions, they are still at a very low level, and they have a lot of details in those basic functions. Right? So still a programmer or just a user of a computing system is not able to understand what are these functions. And if I just give you some of these functions, it takes a lot of time for you to write code. Right? So what you do is you have further level of abstractions. So using these drivers, on top of them, you write some code, maybe assembly level code, right, using the functions, and you develop system calls. Right? So that is where the system calls lie. System calls lie on top of the drivers, right? Because the drivers give you a little bit of abstraction, so give you nice functions, and using those functions, the basic functions of those hardware, you write system calls. Right? Now, just the system call doesn't work. If you want a kernel, then what you have is you have to have this hierarchical structure of an operating system kernel. Right? So here this is, we are making the resident monitor that we had and dissecting it and seeing what are the different components of the resident monitor. Right? Now at this point we are giving it a new name. We are giving it kernel. The name kernel. Right? Now we will also see what is the difference between kernel and OS a little bit later. So now if you have kernel, the first thing that you have is device driver, then you have a lot of system calls. What are these system calls? So these system calls are the interface between different components of the resident monitor. Right? So these are these components. You have these components, and then on top of these components you have the system call, right? So what are these components? The first thing is the CPU scheduler. CPU scheduler, how do you do it? You write assembly level code for CPU scheduler. So using the device drivers, using the nice functions that the device driver gives you, using those, combining those, you write a CPU scheduler. Then you write a memory manager. Right? These are all code that you are writing. So you write a CPU scheduler, you write a memory manager, you write a disk manager, you write a network manager. You write all these things. Now, what do you mean by writing all these programs? So you write these programs, and then what is the interface for these programs? How do you use them to run an operating system? So these programs are also called APIs. Right? So these are APIs. These provide you APIs. So APIs means what? Again, a set of functions. Right? Again, a set of functions, but these functions are a little bit higher level than the functions that the device drivers give you. Device drivers give you a lot of basic functions, but combining these functions, the scheduler, memory manager, network, disk, they give you higher level functions. Right? Now, how to interface between system calls, which are actual functions that you can use and write your code, versus the functions that these or the APIs that the network scheduler memory manager give you. The interface is called file systems. So file systems forms an interface between these two. So what happens here is that everything, the scheduler, memory manager, network, disk, device drivers, everything is a file in your operating system or resident monitor for now. Everything is a file. So if you have a file, you have to have proper naming conventions of those files. You have to read those files. Right? You have to execute those files. So all those functions are managed by the file system manager. Now once you have the file system manager, it gives you functions that the system call can use and write higher level functions. So the combination of system call, file system manager, network, disk, scheduler, memory manager, device driver, those make a Linux kernel or whatever kernel, right? Or Windows kernel. So now I have two errors. I have hardware interrupts here and I have software interrupts there. Right? So there are two types of interrupts. So whatever events are generated from a hardware, corresponding to every event, you have the device driver has to have a handler corresponding to every event. That is the task of the device driver writer, whoever is writing the device driver. Whoever is manufacturing the hardware has to write the device driver. And it has to make the device driver so generic that any Linux kernel can use this. Not I'm just saying Linux, but in Windows also. Any kernel can use this. Right. You have to have those generic functions, yes.
So are the device drivers stored on the device itself, or like are they?
No. So those have to be part of the OS kernel. The device drivers have to be part of the OS kernel. But the device drivers are provided by the manufacturers.
Wait,
So you give a device and you also have to give a software for that device. That software is the device driver.
So like if I got a mouse and then like I plug it into my computer, does it automatically load the device driver on my
So
kernel?
that is a what?
That one's a bit different.
That is a bit different, but no. Conceptually, it should not be that different. Conceptually, you are right that you have to contact the mouse manufacturer and get the software for it. But they have streamlined the process. So now what you can do is any mouse will have the same type of driver that every other mouse has. Right? So those type of drivers can be put in the kernel, OS kernel, and that can be a generic type of driver. Now the manufacturer has to just interface between that generic type of driver and whatever he wants to do with the mouse. So that process is streamlined, but conceptually yes, you have to go to the manufacturer and get a driver, right, and put it into your kernel. But they have streamlined the process. So now these are hardware interrupts. These are managed by the device drivers. Now using all this scheduler, memory manager, disks, network, you have system calls. So system calls are called software interrupts, or they generate software interrupts. Right? So the function of Linux kernel, I'm still saying Linux. Anyway, the function of any kernel is to convert hardware interrupts into software interrupts. That is kernel. Right? Now what is OS? What is operating system? A lot of people have disagreement between these two terms, operating system and kernel. Some people say that operating system is the kernel. Some other researchers say that no, operating system is not the kernel. Now, if you are very familiar with coding and kernel programming, then if I give you a CPU system or a computing system and I just give you a kernel, you should be able to run whatever you want. Right? You don't need anything else. If I give you a kernel and a computing system, you can run anything in this world, any application you can run. But the problem is, not everybody is proficient with kernel coding, right? Kernel programming. So if I am not very proficient in kernel programming, So if I want to use a computing system in day-to-day life, I cannot work with software interrupts. Right? So I have to work with nice, visually pleasing interfaces. Right? I need folders, I need desktop backgrounds, I need some program that controls my network, connects to Wi-Fi automatically. All these things I need, because if I don't have, I cannot use the operating system. Those are called modules, kernel modules. Right? So modules means what? They will use the system calls. They'll make some combination of the system calls and give you even further higher level functions. And these higher level functions are very intuitive to the user. So using the system calls, the modules will develop a nice desktop background. They will develop a nice folder structure. Right? Those are all things that you need to interface with the computing system. In order to use a computing system, you don't need anything else. It just the kernel suffices. But if you want to have a nice interface, then you need kernel modules. Right? So people say that many researchers say that operating system is kernel plus kernel module. Right? Yes.
So command line interface is just a module then, just a kernel module at that point?
Command line interface?
Yeah.
Yes. So operating system is kernel plus kernel modules. Now what you have to do is kernel modules you cannot really change. You have to take kernel modules and you have to combine with the kernel, and then you get an operating system. Right? So that is the whole, that is the distinction between kernel module and operating system. Right? So now there are different types of operating systems, many different types of operating systems. A general purpose operating system is where we will focus our discussions on. But there are other types of operating systems: real-time, embedded, distributed, virtual, all those kind of operating systems. So we will just briefly mention what are the different types of operating systems. Right? So general purpose, we are talking about it, so no need to discuss that. And anybody know what is real-time operating system? Yeah. Then what is embedded operating system?
Well, I guess if you don't have operating system, it doesn't really have, like you can immediately access memory and change bits and stuff. There is no layer between you and memory for it to affect.
No, it's a slightly different concept. Can you give an example of where a real-time operating system is used?
Like a serial.
What?
Like a serial, there's serial operating system.
Serial?
No, serial. It's a family.
I don't know that.
It's okay. It's a piece of hardware.
Okay.
I think it's a real operating system, but I'm not sure if we're talking about the same thing.
So real-time operating system, the main idea behind having a real-time operating system is any application that you run in that operating system has a corresponding time within which it has to finish. Right? If that whatever system you are talking about, does that use it like that, or I am not familiar with that system. So that is real-time operating system. Real-time operating system means if you want to run an application successfully, it has to finish within a certain amount of time, and this time can be varied for different applications. So if you cannot finish within a certain amount of time, then the operating system fails. Right? Now, is your laptop operating system real-time? No, right? Because I don't care about how long it takes. I mean, I care in a general sense, but it's not a life-threatening problem if my application does not run within a certain amount of time. Right? But in real-time operating system, it is a threatening problem. So, example is operating system in an aircraft, right? So let's say cruise control. In an aircraft, you have cruise control, and you said that, okay, I need to stop cruise control because I need to turn the aircraft some degrees. Now you gave the command of stopping cruise control, and you also give the command of turning. Now that has to finish within a certain amount of time. It cannot take 10 minutes to finish. Right? If it takes 10 minutes to finish, then instead of going to Australia, you go to South Korea. So that is a big deal. So that's why you have to have real-time. That's why you need to have real-time operating system. Now, embedded operating system is what she was saying. That what is embedded operating system? Now we have all these different types of computing systems that are that we wear or maybe embedded in some devices. Let's say this one, right? There is a nice display, and if I click this, I can control all these things. Right? This is not a general purpose computing system. I cannot run C code in it, or I cannot run Microsoft Word in it. But it still does some computation. It's a stripped down version. It's a stripped down version of a general purpose computing system. So that is an embedded computing system. This is wherever, whatever thing I can see, I embed computing into that. So that is embedded computing system. Yes.
Just wanted to clarify that in this class we'll consider like either cars, phones, or like TVs as embedded systems because that's what we do, or like medical devices. Because
Yes.
that's what we did in 360. I just wanted to.
They did what?
In 360 we considered cars, TVs.
Yes, exactly.
phones.
Cars, TVs, wearable computing systems, so medical devices, as you were saying.
Okay,
Yes.
so-
So those are embedded computing systems. Microwaves. In microwaves, you can input how much time you want to warm a food, right? So that is also embedded computing system. Yes.
I'd assume in say something as simple as a microwave, it would take the same amount of cycles to accomplish better loss every time. How is that different from real time?
So in microwave, you don't care whether. So you are giving 30 minutes, fine, but that operation, that application that you run, is very deterministic. It is not dependent upon input data, right? Now, applications in the example that I gave, aircraft, cruise control, that is dependent upon input, right? How much degree, how long, speed, yes, right? So that application is dependent upon input. So how long that application runs, you don't know, right? You don't know how long it will run. But in a microwave, you know exactly, okay, 30 minutes means it will run 30 minutes. I don't care whether the food is warm enough or not, right? But in this case, it's as if saying that the food, you give microwave an input that I want to warm the food to 70 degrees. Now run and finish it within 5 minutes. Now that's a real-time application. Because if it doesn't finish within 5 minutes, either I have cold food or I have burnt food. Right? So that is real time. When if you tell a microwave that thing, that you want to warm my food to 70 degrees and do it within 5 minutes, that is real time. But you don't say that. Right? You just say that, okay, 30 minutes you warm it. I don't care what temperature. So that is not real time microwave. Yes.
So I assume that real-time operating systems are much more, like, a lot more expertise needed to work with them because of something. goes
Yes,
wrong.
real-time operating systems are often used in safety-critical applications. So, for example, another example is robotic arms, right? Used for surgery. So you give a poking instruction or incision instruction, and then you only do it this much, but the robotic arm does this much. Big deal.
Wouldn't you consider real-time operating system as a subcategory of embedded operating systems? Because
You can,
it's
yes,
embedded-
exactly. You can consider. But there is a slight difference because embedded computing system does not automatically imply that you have a time restriction.
You can have general purpose real-time operating systems.
Yes, you could. You could have general purpose real-time operating systems as well. So you can have combinations of these. Then what is distributed computing system or not computing system? Distributed operating system. Any idea what is distributed operating system? What?
Clusters.
Clusters, yes, exactly. Clusters, cloud computing. Right? So what are clusters? You have this room full of computing systems. They are networked using some wires. Right? So you can use whatever CPU you want. Let's say there are 500 CPUs. You can use whatever CPU you want to run your code, and the data that you run may not be in that particular CPU. So let's say you are running computation on a particular CPU here, and your data is in some disk that is on that corner. Since they are networked, you can run it. So it's like a room full of computer, but executing as one single computer. So that is distributed execution mechanism, and the operating system that enables that distributed execution is distributed operating system. Right? Virtual, that you all know. I am assuming virtual operating system. What is that? Yes.
Virtual box.
Yes, virtual box. So what is it?
The service runs on like a server, and it just,
May not be a server. May not be a server. Yes.
Is it like an operating system that's not directly run on hardware and it's a little like simulated by hardware?
Yes, it's kind of like simulated. Yes. So what he is saying that a virtual operating system is some operating system that is simulated. Right? So let's assume a Linux system, and let's say you don't want to use Linux. You use VirtualBox and you run Windows on it. How did you do that? Right? So it's basically simulation of Windows on Linux system. So how do you do that? It's very simple. What you need to do, and it's very simple because of this kernel structure, right? Kernel and modules. That's what we have in operating system. Kernels and modules, right? Now this scheduler, memory manager, network, disk, file systems, that may be just part of the Linux system. But the system calls between Windows and Linux is different. Right? So what you need to do is you just need to convert the system calls of Windows to system calls of Linux. And who does that? You need something called a middleware. Yes, you are saying? No. Okay. And that middleware was called a long time back hypervisor. Right? You had some question?
Is a virtual system and an emulator the same thing? Because you were saying how you can emulate a Linux and a Windows or whatever.
No, there is
Is there a difference between
slight difference. There is a slight difference between emulator and a simulator. I'll answer this question later. Because we will come to this when we are talking about scheduling. Or no, rather not scheduling, when we are talking about virtual memory. We will come back to this. So I'll answer that question then. Yes?
Is virtual different from embedded and distributed, or is it a type of both?
No, it's different. Virtual is different. Embedded and distributed, you don't simulate anything. Right? You don't simulate the execution of another operating system. But virtual means that you are running Linux underneath, but as an interface you are seeing Windows. So that means you have to have some conversion between the system calls. So this discussion finishes our first module. Now let's go on to the second module. So now we will talk about CPU scheduling, which is I believe chapter 4. CPU scheduling is I think chapter. Oh, by the way, if you want to for your exams, you go to content, you go to book chapter. There is tentative book chapters. Study these, right? So these are the chapters that are needed for your exams. The others you can study for other purposes, for example, interview questions or all that. But for your exams, those are the chapters that will follow. Yes.
So does module 1 correspond to chapter 1?
Yes. No, chapter 1 and I think, okay, I'll go.
The exam, there's stuff from the book that wasn't covered in that.
No stuff from the book that isn't covered. In exams, you always have questions from whatever is covered, whatever we have discussed. Okay? What is that? What?
The slides or what's the best source for it?
No, not only the slides, book and the lecture. Okay, so let's continue. Very short time here, 2 minutes. I want to discuss one concept. I want to just discuss one concept and then you can go. There are two terms, programs and processes. Right? Programs and processes. Do you know the difference between programs and processes? What is a program? What is a process? Yes? Yeah. Process is what? A program is also run on hardware.
Processes run programs.
Processes run programs. Very good sentence. So programs is whatever you write as code using high level language, maybe C or Java, whatever you wrote. Now that program is just a very inactive piece of file. Right? It's just a file. You cannot run it. You cannot run a program. Now the action of running a program is called a process. So you have to have some mechanism to convert this inactive passive file into something that is running. That action is called a process. The action of converting a program and then taking it and running it is called a process. So there are a lot of steps involved in between this program and a process. Right? So what are the steps? The first step is you have a high level language, you have to convert it into assembly. Otherwise the computer doesn't understand. So how do you convert from high level to assembly? Compiler, not only compiler. No, not loader. Conversion does not involve loader. It's linker. So you use compiler, you use linker to convert a program into assembly. Now even if you convert a program into assembly, or that is bits, you still cannot run it. Why? Because you need to give it memory. So who gives you memory? The loader gives you memory. The loader takes the binaries and puts it into memory. Even if you have put a program into memory, you still cannot run it. You have to run it by creating a process. Right? What does that process do? It follows a lot of mechanisms to do basically two things. First, take the first line of code, the address of the first line of code, put it into program counter of the CPU. Second, save the state of the program. Why? Because you might want to switch between programs. If you switch between programs, you don't want to start the program all over again. You want to continue from where you left off. So you have to store the state. That state is stored in status register. We'll talk about that later. Now you And you do all classes.
Yeah, totally.
Not today, from Monday. TVS known, but oh yes, because it cannot, doesn't let you
But I'm sure there's a lot of different.
I just want to know, presentation starting
No, Mondays.
I've gone both ways.
You have one, two, that's, I think I discussed that project, when we assign
Because I went yesterday to the 6 p.m. session and everyone was in there. Everyone went.
everyone went?
Yeah, except obviously the TA wasn't there, so they left.
Because I think told the team to go to the presentation, from Thursday. There might have been some confusion.
I think, like you said on Wednesday that you post up the assignment on Thursday, so I think people thought they were supposed to be there, but.
Oh, okay, so, okay, I'll clear that confusion.
Okay.
I'll post an announcement to you.
Okay, thank you.
I was just gonna ask you, do you allow any hiccups for the test or anything else? 'Cause I'm supposed to be out of town next Friday through Monday.
Oh, okay, no, so then what you do is you can take it later,
Okay,
so you can come Wednesday and take the exam.
okay, just between class or something,
Yeah, during office hours, so like around 1:30.
is there any way I could do it, I have a class at 2, so.
So you
is there
just
any way I can come
email
on
me and set up time.
Monday? Okay, I know that's horrible.
What?
Just, I know that's horrible, it's just the one weekend I kinda had
That's
booked
fine.
before the semester started, so.
No problem. You just email me and set up a time.
Okay, that's good. I've got people flying in from out of town to go up somewhere, and I'm like, oh, they're gonna kill me if I cancel.